In this video, we're going to summarise the steps we had to take with the CORDIC algorithm in order to generate the functions that we've seen throughout this course. We're going to start off with the sine, the cosine and the tangent. We were able to generate the cosine of an angle theta and the sine of an angle theta using the same step. So the setup was m is equal to 1. This would ensure that we are in circular. And then we used the rotation mode. The initialization, we have x0 is equal to the value 0.607, y0, 0 and z0 is the angle theta we wish to find. And the output xn will give us our cosine of that angle theta, and yn will give us the sine of that angle theta. Now if we wanted to generate the tangent function, we know that the tan can be written as the sine theta upon cos theta, so we have to go through the division. So the setup is we follow step 1 in order to get the cosine and then the sine. We set m is equal to 0, so we're now in linear and in vectoring mode. We use the initialization x0 and y0, which will be the output of the first step here, which in effect would be our xn here and the yn here. And we set z0 is equal to 0. And this is going to give us an output zn, which is z0 plus y0 upon x0. But we know our z0 is set to 0, so our final output is just going to be the y0 upon x0. And that's going to be our sine theta upon cos theta, which will give us our tan theta. So that's us able to generate the first three functions, sine, cosine and tangent. Now we want to generate the inverse of the sine, the cosine and the tangent. So the first one here is going to generate the inverse sine, and the second one generates the inverse cosine. The setup is m is equal to 1, so it's circular, and it's in vectoring mode. We have x0 is equal to 0.607, or y0 is 0, z0 is 0, and we have this extra factor yn is equal to some value c. Now it's going to give us the final output, which is going to be our arc sine of our c upon anx0. So this is going to give us our arc sine function. And similarly for the arc cosine, we can use the setup m is equal to 1 in circular, and it's vectoring mode. In this case here, we set y0 is equal to 0.607 and z0 is equal to 90 degrees. And the value for our xn is equal to some value c. And it's going to give us the arc cosine of c upon any naught. So let's look at the final one, which will be our arc tangent. So for our arc tangent, our setup remains the same. M is equal to 1, so it's circular, it's in vectoring mode, and we have our x0 and y0 are values x and yn, and z0 is equal to 0, and this will give us the arc tan of y0 upon x0. Now we were able to do polar to rectangular and rectangular to polar coordinate conversions, and we did this just by reinterpreting what we have already done before. So in order to go from polar to rectangular, that is, we're going from r and theta to some rectangular values x and y. Then with the setup is m is equal to 1, so we're in circular, and if we use it in rotation mode, we can set the x0 is equal to 0.607 and the z0 is the angle of theta. So in effect, this value here is a value for our r, and this value here is a value for our theta. And when we work through the algorithm, we're going to get the output, which is going to be the value of cos theta, but it's now going to be r cos theta, and the value of r sin theta. So this r cos theta and r sin theta is going to give us the x and y components. So we've gone from r and theta to a value of xn and yn. Now similarly with the rectangular to polar, our setup is m is equal to 1, so we're in circular, but this time we're using vectoring mode. The value for our inputs are x in and y in, so we're going from the polar values x and y, and we're heading over to we start off with the rectangular components x and y, and we're heading over to the polar coordinates r and theta, such that the output xn is going to give us the root of net x0 squared plus y0 squared times this an. So in effect this here is a value for our r. And the angle theta is going to be the arctan y0 upon x0. So this is our angle theta here. So this is just a reinterpretation of the circular, rotation and vectoring modes, giving us the polar to rectangular and rectangular to polar conversion. We can also perform multiplication and division. The setup is m is equal to 0, so we're using linear, and if we're in rotation mode, the initialization values x, y and z will give us a final output yn, which is equal to y0 plus x0 times z0. So this is the multiplication here. Of course we can set the value for y0 to a value of 0, and we just get the final output x0 times z0. Now again for the division, we're in linear, but now we're using vectoring mode. And the inputs are going to be x, y and z. And the final output we're interested in is the zn, and it's equal to z0 plus y0 divided by x0. So this is the division. Again, we can set the value for our z0 is equal to 0, and it will just give us the value zn is equal to y0 upon x0. So that's the multiplication and division. We can work out the reciprocal by using the linear and vectoring mode. In this case here, we set the value for y0 is equal to 1, and the value x0 to the value x, and the value z0 will be the value 0, and this is going to give us the output zn is equal to 1 upon x0. So we're going to get the reciprocal of the value x0. Now we can generate the hyperbolic sine, cosine and tangent using the similar process we used for the sine, cosine and tangent. In this case we're going to be using hyperbolic. So the setup in order to generate the cos theta and the sin theta is m is equal to minus 1, so this will give us hyperbolic, and we're going to use this in rotation mode. We set up our x0 is equal to the value 1.20749, and the output xn and yn will give us our cos theta and our sin theta. Now in order to generate the tan theta, we're going to use the identity. Tan theta is equal to sin theta upon cos theta. So we're going to do step 11 in order to get the cos theta and sin theta, and then we're going to do step 6. Now step 6 was the division using the linear mode, so I've written this down again. The value m is equal to 0, so we're in linear and we're using vectoring mode. Now the input here for our x and y is going to be the output from the previous stage, which is our value for our cos theta and our sin theta for x0 and y0. The final output is going to be the value Zn, and it's going to be y0 upon x0, assuming that we've set this value z0 is equal to a value of 0. We will get the value Zn, which is sin theta upon cos theta, which is our tan theta. So that's us able to generate our three basic hyperbolic functions: sin, cos and tan. We can generate our inverse hyperbolic tangent using m is equal to -1, so we're in hyperbolic and we're in vectoring mode. The final output Zn is going to give us the arctan y0 upon x0. Now, in order to generate the inverse hyperbolic cosine and sine functions, we're going to have to use a few extra processes. So let's have a look at those processes next. We can generate the square root by choosing m is equal to -1, so this is hyperbolic and we're in vectoring mode. For the initialization, we set x0 is equal to a plus 1 upon 4an squared and y0 is equal to a minus 1 upon 4an squared. This will give us the final output xn is equal to the square root of the value a. To generate the natural logarithm, we're going to use two steps. So we're going to start out with m is equal to -1, so we're in hyperbolic and vectoring mode. We say x0 is equal to a plus 1, y0 to a minus 1, and z0 to a value of 0. The final output for the value Zn will tend towards a half ln. So we're not quite at the natural log of our input a, we've got a value of a half. But we can get rid of that value of a half by using step 9. So we can divide this throughout by a half. So we'll have a half divided by a half, which is a value of 1. So step 9 is the division. We say m is equal to 0, it's in linear and in vectoring mode. We say x0 is equal to 0.5. The value for a y0 is going to be the output from the previous stage, which is the value over Zn, which is our half ln. This will give us a final output here, which will be a value Zn. And if we set z0 here to 0, it's going to be y0 upon x0. So this is going to be a half ln divided by a half, which will just give us an output of ln. In order to generate the inverse hyperbolic cosine and the inverse hyperbolic sine functions, we're going to have to use a more complicated process. We're going to have to generate the function ln a plus the square root of a squared minus 1 in order to generate the hyperbolic cosine function. So we start off with step 13, which is m is equal to -1, it's hyperbolic and it's vectoring mode. The initialization x0 is equal to a, y0 is equal to 1, and z0 is some value zn, which we don't really care about. The output we're interested in is the value xn, and that is equal to an, the square root of a squared minus 1. So we take this here and we pass it on to the next stage. Now the next stage is the same as step 9. M is equal to 0, it's linear and it's in vectoring mode. And we're doing a division by this value an. And we're also adding on a factor of a. So the value for x0 is a value an. the value for y0 is the output from this stage here, which was the value xn, and the value for z0 is equal to the value of a. Now the final output is going to be z0 plus y0 upon x0. So the final output zn is equal to a plus the square root of a squared minus 1. Now we're going to have to take the natural log of this value. So step 15 was the natural log. M is equal to minus 1. It's in hyperbolic and vectoring mode. The input is a plus 1 and the input y0 is a minus 1 and the input z0 is equal to 0. Now when we work through this here, the value for a is going to be the output from the previous stage. This will give us the final output Zn is equal to half ln a. But of course we want to get rid of the half, so we're going to have to divide by a half in order to get rid of this. And we do that using step 9, which has the value m is equal to 0 and it's linear vectoring mode. x0 equals 0.5, y0 equals the output from the last stage, which is this half ln a. And the final output is going to be given by the value Zn, which is equal to ln a plus the square root of a squared minus 1. And this is going to give us the inverse hyperbolic cosine. In order to generate the inverse hyperbolic sine function, we're going to have to generate the function ln a plus the square root of a squared plus 1. So the only difference between this hyperbolic sine and hyperbolic cosine is the first CORDIC step. So the first CORDIC step is circular and it's in vectoring mode, and this is the step we see in step 5. And we can set the value of x0 is equal to 1, y0 is equal to a, and this is going to give us the output, which is going to be an, the square root of x0 squared plus y0 squared. So this output here then gets fed into the input of the next stage, and the next stage here is going to be linear vectoring mode, and we're going to be getting rid of this term of an, so we're going to do the division. So x0 is an, y0 is the output from the previous stage, which is this value here, and z0 is equal to a. So we're going to be left with Zn is equal to a plus the square root of a squared plus 1. Now we have to go and find the natural log of this. Now to find the natural log, we use our step 15, which is going to give us the value half ln a. And then this output here gets fed into the final input, which is step 9, which is linear vectoring mode. And this is going to give us the final output, Zn, as a natural log of a plus the square root of a squared plus 1. And this is our inverse hyperbolic sine function. The previous two examples were the inverse hyperbolic sine and the inverse hyperbolic cosine. I don't believe I actually numbered those, but those were 16 and 17. Now the next one is number 18, which is the exponential function e to the x. And we're going to set m is equal to minus 1, so it's going to be hyperbolic, but we're going to be using the hyperbolic in rotation mode. We're going to have z0 as an angle of theta, and x0 and y0 are the constants here, 1.20749. This is going to give us an output, xn and yn, which are both e raised to the power of x. In order to generate the more general exponential a raised to the power of x, we're going to have to use the identity e raised to the x ln a is equal to a to the x. So we have to generate this. Now we generate this in 3 stages. we use step 15, which is hyperbolic vectoring mode. We say x naught is equal to a plus 1, y naught is a minus 1, z naught is 0. And this is going to give us the output value a half ln a. We then go on and use step 8, which is linear rotation mode. We put a value in for our x naught, which is twice the value of a. Now again, this is a different a from this value here. This is a new choice of our value a. And the value y naught is 0, and the output from the previous stage here is a half ln a. So z naught is equal to half ln a. And this is going to give us the multiplication x naught z naught, which is going to be the multiplication of x times ln a. Now this new value for x is nothing other than this value here, because we're going to be multiplying it by the value 2, which will get rid of this half here, and then we'll have the value of a. So we'll just call our new output a, we'll call it the value x. So we're going to have x ln a here generated. Now we're going to have to raise this to the power of e. So we use step 18, which is hyperbolic rotation mode. We set our x naught and y naught to these values here, and our input z naught is the output from the previous section, which is the x ln a. The output then is going to be the value of e raised to that power of the input x. So the input x here is now this x ln a. So that's e raised to the power x ln a, which is none other than the function a to the power of x. Finally, we can generate another 6 functions, which are going to be the reciprocal of the sine, the cosine and the tangent, and the reciprocal of the hyperbolic sine, hyperbolic cosine and hyperbolic tangent, simply by generating the sine cos tan or the sine cos tanh and following it with the CORDIC algorithm that gives us the reciprocal 1 upon x. So that's covered all of the functions that we've generated using the CORDIC algorithm in this course. That's all for this video. Thank you for listening, and goodbye.